Hello, class, and welcome to Chapter 8, Section 3, where we'll talk about different bonding theories. So molecular orbitals, the model you have been using for covalent bonding assumes the orbitals are those of the individual atoms. There is a quantum mechanical model of bonding, however, that describes the electrons more in molecules using orbitals that exist only for grouping of atoms. And when two atoms combine, this model will assume that their atomic orbitals will overlap to produce more of a molecular orbital or an orbital that applies to the entire molecule. And in some ways, atomic orbitals and molecular orbitals are similar. Just as an atomic orbital belongs to a particular atom, a molecular orbital belongs to a molecule as a whole, and a molecular orbital that can be occupied by two electrons of a covalent bond is called a bonding orbital. So a sigma bond, this is when two atomic orbitals combine to form a molecular orbital that is symmetrical around the axis connecting two atomic nuclei. And this is called a sigma bond. Its symbol is the Greek letter sigma, as you can see right there. So that's a sigma bond. Sigma bonds are covalent bonds that result from an imbalance between the attractions and repulsions of the nuclei and the electrons involved. The nuclei and electrons will attract each other. Nuclei will repel other nuclei, and electrons repel other electrons. In a bonding molecular orbital of hydrogen, however, the attractions between the hydrogen nuclei and the electrons are stronger than the repulsions, and the balance of all the interactions between the hydrogen atoms is thus tipped in favor of holding the atoms together. And the result is a very stable diatomic molecule of H2, of hydrogen. Atomic p orbitals can also overlap to form these molecular orbitals. A fluorine atom, for example, has a half-filled 2p orbital. And when two fluorine atoms combine, the p orbitals will overlap to produce a bonding molecular orbital. There is a high probability of finding a pair of electrons between the positively charged nuclei of the two fluorines. The overlap of those two p orbitals produces a bonding molecular orbital that is symmetrical when viewed around the fluorine-fluorine bond axis that connect the nuclei. Therefore, that fluorine-fluorine bond is also a sigma bond. Then we have pi bonds. So in the sigma bond of the fluoride molecule, the p atomic orbitals overlap end to end. In some molecules, however, orbitals can overlap side to side. And the side-by-side overlap of the atomic p orbitals produce what are called pi molecular orbitals, as shown here. So we have a pi bonding molecular orbital. These pi bonds, symbolized by the Greek letter pi, the bonding electrons are most likely to be found in the sausage-shaped regions above and below the axis of the bonded atoms. And because the atomic orbitals in pi bonding overlap less than in sigma bonding, pi bonds tend to be weaker than sigma bonds. Electron dot structures fail to reflect the three-dimensional shapes of these molecules. The electron dot structure and structural formula of methane, for example, shows the molecule as if it were flat and merely two-dimensional. In reality, methane molecules are three-dimensional, and this is where we get into the VSEPR theory. The hydrogens in a methane molecule are at the four corners of a geometric solid called a regular tetrahedron. In this arrangement, all of the bonding angles are 109.5 degrees, and that gives us a tetrahedral angle. So that's what methane looks like. In order to explain this three-dimensional shape of molecules, scientists use valence shell electron pair repulsion therapy, VSEPR, V-S-E-P-R theory. This theory states that the repulsion between electron pairs causes the molecular shapes to adjust so that the valence electron pairs stay as far apart as possible. Unshared pairs of electrons are also important in predicting the shapes of molecules. For example, in ammonia, NH3, it's surrounded by 4 pairs of valence electrons. However, one of the valence electrons pairs is an unshared pair. No bonding atom is available for these unshared electrons, so they're held closer to the nitrogen than are the bonding pairs, and the unshared pair strongly repels the bonding pairs, pushing them together. And that's how we get this shape of ammonia, NH3. The measured hydrogen-nitrogen-hydrogen bond angle is only 107 degrees, rather than the tetrahedral angle of 109.5 degrees. In a water molecule, the 2 bonding pairs and the 2 unshared pairs of electrons form a tetrahedral arrangement around the central oxygen. Thus, the water molecule is planar or flat, but bent. With these 2 unshared pairs repelling those bonding pairs, the hydrogen-oxygen-hydrogen bond angle is compressed to about 105 degrees. So those unshared pairs of electrons that aren't involved in the bond will kind of push the bonds away from them, and that will make these molecules kind of appear to be at an angle. The carbon in a carbon dioxide molecule has no unshared electron pairs. So the double bonds joining the oxygens to carbon are farthest apart when the oxygen-carbon-oxygen bond angle is 180 degrees. So CO2, carbon dioxide, is a linear molecule. So here are some common molecular shapes of these molecules, and it's kind of interesting to see them all here: linear, trigonal planar, bent pyramidal, tetrahedral, trigonal bipyramidal, octahedral, and square planar. The VSEPR theory works well when accounting for molecular shapes, but it does not help much in describing the types of bonds that are formed. Orbital hybridization provides information more about both molecular bonding and molecular shape, and in hybridization, several atomic orbitals mix to form the same total number of equivalent hybrid orbitals. Hybridization involving single bonds. So for example, the carbon atom's outer electron configuration is 2sp and 2p2. As you can see, this outer electron configuration has these 4 electrons. But one of the 2s electrons is promoted to a 2p orbital to given 1 2s electron and 3 2p electrons. The 2s and the 2p bonds are all identical, and the 1 2s orbital and those 3 2p orbitals of a carbon atom mix to form 4 sp3 orbitals, all at that tetrahedral angle of 109.5 degrees. So here we have this example: hybridization involving single bonds in methane. Each of the 4 sp3 orbitals of carbon overlaps with a 1s orbital of hydrogen, and that will form this angle of 109.5 degrees between those atoms. Hybridization involving single bonds. The sp3 orbitals will extend farther into space than either the s or p, allowing a great deal of overlap with the hydrogen 1s orbitals, and the extent of overlap results in unusually very strong covalent bonds. Hybridization involving double bonds. Ethene is a relatively simple molecule that has 1 carbon-carbon double bond and 4 carbon-hydrogen single bonds. Hybridization involving these double bonds in ethene, the sp2 hybrid orbitals form from the combination of 1 2s and 2 2p atomic orbitals of carbon, and this makes for each hybrid orbital to be separated from the other by 120 degrees. And we can see that shown here, the 120-degree angle. These are atomic orbital and hybrid orbitals of a carbon atom, showing the sigma bonds and the pi bonds. And this is looking at double bonds. In ethene, these 2 sp2 hybrid orbitals of each carbon form the sigma bonding molecular orbitals with 4 available hydrogen 1s. Sorry about that, everyone. I had to sneeze. The third sp2 orbitals of each of these 2 carbons will overlap to form a carbon-carbon sigma bonding orbital, and the 2 p carbon orbitals overlap side by side to form a pi bonding orbital. Triple bonds. A third type of covalent bond is a triple bond, which is found in ethine, which is made of 2 carbons and 2 hydrogens, also called acetylene. Ethine or ethene is a linear molecule, and the best hybrid orbital description is obtained if a 2s atomic orbital of carbon mixes with only one of the 3 2p atomic orbitals, and the result is 2 sp hybrid orbitals for each carbon. You can see that here. In an ethine molecule, 1 sp hybrid orbital from each carbon overlaps with a 1s orbital of a hydrogen to form a sigma bond, and the other sp hybrid orbital of each carbon will overlap to form a carbon-carbon sigma bond. So then the 2p atomic orbitals from each carbon also overlap. I know this is a lot of information and it's a little confusing, so I would encourage you guys to read your textbook well. Maybe watch this lecture again, and we'll review some of these concepts in the next section as well. Thank you for listening.